10 million years ago, a world existed that we can barely comprehend. A planet both familiar and alien, where the continents we know had shifted into recognizable positions, yet the landscapes remained dramatically different. Imagine standing at the edge of a vast grassland that stretches beyond the horizon. The air feels different, richer in oxygen, heavier with moisture, carrying scents your brain struggles to categorize. No human has ever breathed this air. No human eyes have witnessed this landscape. We are separated from this lost epoch by an immeasurable gulf of time. 10 million years. The number itself feels abstract, clinical. But consider this. If all of recorded human history were compressed into a single day, the world we're about to explore existed more than 5 years earlier. The creatures that roamed this earth would seem both hauntingly familiar and utterly alien to our modern eyes. Some resembled exaggerated versions of animals we know today, while others defy categorization, leaving only fragments in the fossil record. Scientists call this period the late Miocene. It exists in a curious blind spot of popular understanding, too recent for dinosaur enthusiasts, too ancient for those fascinated by Ice Age megafauna. Yet this forgotten chapter holds extraordinary secrets. What we know of this world comes to us through geological whispers, scattered fossil beds, chemical signatures in ancient soils, microscopic pollen grains preserved in sediment. Together, these fragments form a mosaic of a lost reality. But there's something else. Something troubling about our understanding of this period that few scientists openly discuss. Anomalies in the fossil record, geological inconsistencies, evidence that suggests our timeline might be incomplete. Throughout this documentary, we'll measure the strength of evidence for each claim. Some rest on solid scientific consensus. Others venture into more speculative territory, where mysteries remain unsolved and debates continue. The fossil record should tell a smooth, continuous story. But 10 million years ago, something curious happens. There are gaps, inconsistencies, species that appear suddenly, without clear ancestors, others that vanish without explanation. Could our understanding of this pivotal period be fundamentally flawed? Are we missing critical pieces of Earth's biography during a time when the planet was being reshaped into its modern form? Tonight, we'll journey through time to reconstruct this lost world, examining both established science and the puzzling questions that remain unanswered. What you're about to hear is supported by geological evidence, paleontological discoveries, and cutting-edge research. But it will also challenge some assumptions about Earth's history that you may have long accepted as fact. The stakes are not merely academic. Understanding this period could resolve lingering questions about climate change, extinction events, and even the evolutionary path that ultimately led to our own species. Our story begins in Africa, where the continent's northern edge was drifting toward Europe, slowly closing the ancient Tethys Sea. Mountain ranges were rising, climate patterns were shifting, and life was adapting in remarkable ways. In Europe's forests, ape species were diversifying, some developing adaptations we once believed emerged much later. In North America, vast grasslands supported herds of proto-horses and strange, hornless rhinos. The oceans teemed with life, including massive shark species that dwarfed today's great whites. Ancient whales were evolving rapidly, some reaching sizes larger than any animal alive today. And somewhere, in environments we're still struggling to identify, early hominins may have been taking their first evolutionary steps. This possibility remains controversial, but recent discoveries have pushed back human origins further than we once believed. Tonight, you'll hear evidence that challenges the conventional timeline, fossil anomalies that suggest unexpected connections between continents, geological findings that hint at catastrophic events absent from textbooks. You'll learn about ecosystems that have no modern parallel, environments that existed once and will never exist again. You'll encounter creatures so strange they seem imaginary, yet we know they walked the earth. As we reconstruct this ancient world, we'll separate established science from speculation, fact from theory. We'll examine competing hypotheses and acknowledge the limits of our knowledge. Because here's the extraordinary truth about paleontology. What we know is dwarfed by what remains unknown. Every year, new discoveries force us to redraw the map of the past. 10 million years ago, our planet experienced climate shifts, that transformed entire ecosystems. Understanding these changes has taken on new urgency as we face our own climate crisis. Could the late Miocene hold crucial lessons about Earth's climate systems? Might it provide insights into how rapidly ecosystems can adapt or fail to adapt to changing conditions? These questions aren't merely academic. They speak to our future as much as to our past. So settle in as we embark on this journey through deep time. Let the modern world fade away as we reconstruct a lost epoch, piecing together fragments of evidence to reveal a planet both familiar and alien. Tonight we travel back 10 million years, to a world we never knew but that shaped everything we would become. A world whose echoes still resonate in our bodies, in our DNA, and in the landscapes around us. Chapter 2. Echoes in the Stone. Why does a period from 10 million years ago matter to us today? The answer lies in the subtle but profound connections between that lost world and our current reality. This was the crucible period when our planet's modern ecosystems were being forged. The distribution of species, the patterns of climate, even the flow of ocean currents, all were taking their contemporary form. Yet something happened during this time that scientists still struggle to explain. A global shift occurred, leaving its mark in sediment layers worldwide. The conventional explanation involves gradual climate change, but anomalies in the evidence suggest something more dramatic. If the alternative theories we'll explore prove correct, we would need to fundamentally reconsider how rapidly Earth's systems can change. The implications for our understanding of current climate change would be profound. The late Miocene witnessed one of the most significant ecosystem transformations in Earth's recent history, the widespread expansion of grasslands. This seemingly simple change reshaped evolutionary trajectories across multiple continents. Where dense forests once stood, vast savannas stretched toward the horizon. Species that couldn't adapt vanished. Those that could evolved with remarkable speed, developing new forms, behaviors, and ecological relationships. Consider the ancestors of horses. 10 million years ago, they were undergoing their final major evolutionary transitions. Forest-dwelling browsers were giving way to grassland-adapted grazers. Their teeth changed, their legs lengthened, their hooves transformed. This transformation didn't happen in isolation. Similar adaptations were occurring simultaneously across widely separated regions and among unrelated species. The synchronicity of these changes presents a puzzle we're still working to solve. Traditional explanations focus on climate change driving these adaptations, but the fossil record shows evolutionary leaps occurring more rapidly than gradual adaptation would allow. This suggests other forces might have been at work. Some researchers have proposed that cosmic events, meteor impacts or radiation bursts from our galaxy's center, might have accelerated mutation rates during this period. The evidence remains contested, but intriguing patterns have emerged. What's at stake in this debate isn't just our understanding of the past. If evolution can indeed be accelerated by external forces, our models of how life responds to catastrophic change would need significant revision. This has direct implications for how we assess extinction threats today. Are some species capable of adapting more rapidly than we've assumed? Could others be more vulnerable than current models suggest? 10 million years ago, carbon dioxide levels in Earth's atmosphere were higher than today, but were beginning a long-term decline. Studying this period offers insights into how ecosystems respond to changing atmospheric chemistry. Recent evidence suggests these changes may have happened more abruptly than previously thought. If confirmed, this would challenge our understanding of how stable Earth's climate systems truly are. Ancient soil samples preserve chemical signatures that tell us about rainfall patterns, temperature fluctuations, and even atmospheric composition. These paleosols, as scientists call them, reveal something curious about the late Miocene. They show evidence of rapid transitions, shifts that occurred over centuries rather than millennia. Such changes should leave corresponding marks in the fossil record, with species disappearing or transforming in response. And indeed, we do find such patterns, but they don't always align with the timing predicted by climate models. This discrepancy suggests additional factors may have influenced evolution during this period. One controversial theory proposes that cosmic radiation levels fluctuate as our solar system moves through different regions of the galaxy. During periods of higher radiation, mutation rates increase, potentially accelerating evolutionary change. If this hypothesis is correct, the unusual evolutionary patterns of the late Miocene might be partially explained by our solar system's position in the galaxy 10 million years ago. For you at home, this might seem like an abstract scientific debate, but consider the implications. If cosmic forces can influence evolution, then life on Earth is connected to astronomical cycles in ways we're only beginning to understand. Another crucial aspect of the late Miocene was the changing relationship between predators and prey. New hunting strategies evolved alongside new defensive adaptations, creating evolutionary arms races that transformed species. In North America, early canids were developing pack hunting behaviors that would eventually make wolves such formidable predators. Meanwhile, prey species were becoming faster, more vigilant, and developing novel defenses. The relationship between environmental change and evolutionary innovation remains one of biology's most fascinating questions. The late Miocene offers a natural laboratory for studying these dynamics. Yet there's something peculiar about the fossil evidence from this period. Some species show minimal change despite significant environmental shifts, while others transform dramatically despite seemingly stable conditions. This pattern contradicts our expectations. Environmental pressure should correlate with evolutionary change. When it doesn't, we need to consider alternative explanations. One possibility is that our dating methods for fossils from this period have systematic errors. Another is that we're missing critical environmental factors that influenced evolution. But there's a third, more radical possibility, that biological evolution doesn't always proceed at the steady pace our models predict. Perhaps external triggers can accelerate genetic change in ways we don't fully understand. If this is true, it would challenge fundamental assumptions in evolutionary biology. It would suggest that life's history on Earth has been more punctuated, more episodic than we've recognized. The stakes extend beyond scientific theory. Our ability to predict how modern species will respond to current climate change depends on accurately understanding how they adapted to past changes. If we've misinterpreted the relationship between environmental shifts and evolutionary responses during the late Miocene, our predictions about biodiversity loss in the coming centuries may be significantly flawed. What makes this period particularly valuable for study is that it represents Earth's most recent experience with carbon dioxide levels similar to what we're approaching now. It's our best analog for where we might be heading. The difference, of course, is timescale. Changes that occurred over thousands of years during the Miocene are now happening in decades. This acceleration leaves far less time for evolutionary adaptation. As we journey deeper into this lost world, remember that we're not merely satisfying curiosity about the past. We're gathering insights that might prove crucial for navigating our uncertain future. Chapter 3. Continents in Motion. 10 million years ago, Earth's continents had largely moved into their modern positions, but crucial differences remained. These geographical distinctions created environments and evolutionary pressures that shaped life in profound ways. North and South America remained separated by ocean. Africa was moving northward, slowly closing the Tethys Sea that once separated it from Europe. Australia had broken free from Antarctica and was drifting northward, carrying its unique cargo of marsupial life. This continental configuration created fascinating evolutionary laboratories. On isolated landmasses, life followed distinctive paths. When continents later connected, these separate evolutionary experiments collided, sometimes with dramatic results. The Mediterranean Sea periodically dried up completely during this time, an almost incomprehensible event. Imagine standing on a salt flat that stretches for hundreds of miles, knowing you're walking on what was once and would again become a sea floor. These Mediterranean desiccation events, known as the Mycenaean salinity crisis, left massive salt deposits that remain commercially important today. They also created land bridges that allowed species to migrate between Africa and Europe. In North America, the Rocky Mountains had already formed, creating rain shadows that contributed to the spread of grasslands. The Appalachians, far older, were continuing their slow erosion, gradually altering watersheds and river systems. South America remained an island continent, home to unique mammals found nowhere else. Giant ground sloths, terror birds, and strange hoofed mammals ruled ecosystems that evolved in isolation from the rest of the world. Australia's isolation created perhaps the most distinctive evolutionary laboratory. Marsupial mammals diversified to fill ecological niches occupied by placental mammals elsewhere. The continent was moving northward, becoming progressively drier. Antarctica, recently separated from Australia, was beginning its thermal isolation as circumpolar ocean currents established themselves. Though still warmer than today, the southern continent was cooling, with ice sheets beginning to form. Asia and Europe formed a continuous landmass, though the rising Himalayan plateau, the result of India's ongoing collision with Asia, was altering weather patterns across both continents. These geographical arrangements created climate patterns both familiar and alien. Without an isthmus of Panama, ocean currents flowed differently. The incomplete closure of the Tethys Sea meant Mediterranean circulation followed different patterns. The world was generally warmer than today, though cooling from earlier Miocene peaks. Polar regions had less ice, resulting in lower albedo, reflectivity, and higher sea levels. Forests extended further north than in our time. Areas that are now tundra supported woodlands. Regions that are now desert often featured savanna or woodland ecosystems, yet this wasn't a uniformly lush world. The spread of grasslands represented a type of aridity. Many forests were retreating, creating mosaics of woodland and open country that proved evolutionarily significant. These transitional environments, neither fully forested nor completely open, created selective pressures that favored adaptability. Species that could utilize both habitat types had advantages over specialists. Consider our own lineage. The primates that would eventually lead to humans were adapting to these mixed environments, developing flexibility that would prove crucial in our evolutionary story. The fossil evidence suggests that tree-dwelling apes were beginning to spend more time on the ground in these mosaic habitats. Their bodies were changing, with shifts in shoulder structure, spine, and pelvis. But here, we encounter one of those puzzling gaps in the fossil record. The transitional forms we would expect to find are largely absent. Either they weren't preserved, haven't been discovered, or something more complicated was occurring. This pattern of missing transitional fossils repeats across multiple lineages during this period. It's as if the fossil record is providing us snapshots of before and after, while the middle of the film is missing. Some paleontologists attribute this to the inherent incompleteness of fossilization. Others wonder if evolutionary change sometimes occurs more rapidly than our models predict, creating punctuated equilibrium rather than gradual transition. The late Miocene also saw significant changes in Earth's ocean circulation patterns. As the gap between North and South America narrowed, water flow between the Atlantic and Pacific began to restrict. These oceanic changes had global consequences, altering heat distribution, nutrient cycling, and weather patterns worldwide. Marine ecosystems transformed in response, with some species disappearing while others radiated into new forms. In the North Atlantic, cooling waters were beginning to establish the circulation patterns that would eventually create the Gulf Stream, a current system crucial for moderating Europe's climate. The Pacific, meanwhile, was developing early versions of the El Niño Southern Oscillation, ENSO pattern, that influences global weather today. These nascent climate systems created new selective pressures on both marine and terrestrial life. Earth's atmosphere was changing too. Carbon dioxide levels were declining from earlier peaks, contributing to global cooling and the spread of grasslands. Oxygen levels were slightly higher than today. These atmospheric differences meant fires burned differently, plants grew at different rates, and animals experienced different metabolic demands. The world not only looked different, it functioned differently at a fundamental level. Mountain building processes were active across multiple continents. The Alps were rising in Europe. The Andes were growing taller in South America. These tectonic processes altered weather patterns and created new ecological niches. As mountains rose, they created barriers that fragmented previously continuous populations. Species divided by these new geographical features began to diverge genetically, eventually becoming distinct. This process, allopatric speciation, was occurring simultaneously across many lineages. It represented a major driver of biodiversity during this period, creating the foundation for the species richness we observe today. Yet once again, we find curious patterns in the fossil record. Some species show rapid divergence despite relatively minor geographical separation. Others remain remarkably consistent across seemingly significant barriers. These anomalies suggest that our understanding of speciation processes remains incomplete. The late Miocene offers a window into these dynamics that continues to yield new insights as research progresses. 10 million years ago also marked a significant period in the history of Earth's biomes. Modern ecosystem types were becoming established, though their distributions differed from current patterns. Tropical rainforests were more extensive, reaching further from the equator. Temperate forests grew in regions that are now too cold or too dry. Grasslands were expanding, but hadn't reached their modern extent. These shifting biomes created a complex mosaic of environments. Species adapted not just to specific conditions, but to environmental change itself. Flexibility and adaptability became increasingly valuable traits. The fossil record preserves evidence of these changing ecosystems. Plant remains show shifting forest compositions. Animal fossils reveal adaptations to changing food resources. Soil samples capture signatures of altered rainfall patterns. Together, these lines of evidence allow us to reconstruct the ecological dynamics of this pivotal period. They tell a story of a world in transition, a planet moving from one stable state toward another. Chapter 4. Shadows in the Fossil Record. The fossil record of the late Miocene presents us with a paradox. On one hand, it's relatively recent in geological terms, meaning more fossils have survived than from earlier periods. On the other hand, significant gaps and puzzles remain. These inconsistencies have led to competing interpretations among paleontologists. The conventional view emphasizes gradual change driven by known mechanisms. Alternative perspectives suggest more complex patterns that might require additional explanations. Let's examine some of the most compelling evidence, starting with a remarkable fossil bed in northwestern China. The Hipparian red clay deposits preserve one of the most complete terrestrial records from this period anywhere in the world. These red sediments accumulated continuously for millions of years, capturing a detailed record of environmental change. They show something surprising: several abrupt transitions where ecosystems appear to transform over relatively short time frames. Analysis of fossil pollen from these deposits reveals dramatic shifts in vegetation, from forest to grassland and back again, occurring within what appears to be a few thousand years. This is faster than expected for climate-driven changes. The animal fossils tell a similar story. Species adapted to forest environments disappear suddenly, replaced by grassland specialists. Later, the pattern reverses just as abruptly. Traditional explanations attribute these shifts to climate change, but the rapidity of transition has led some researchers to propose additional factors, perhaps changes in fire frequency, disease outbreaks, or even extraterrestrial influences. Similar patterns appear in North American fossil beds from the same period. The famous Coffee Ranch site in Texas preserves an ecosystem from approximately 6.6 million years ago that shows evidence of rapid transition. Here, researchers find a curious mix of species, some showing adaptations to woodland environments, alongside others clearly evolved for open grasslands. This suggests they were captured during a transitional phase, but the transitional forms we would expect to find, species partway through evolutionary adaptation, are largely absent. Instead, we see fully woodland-adapted species and fully grassland-adapted species, with few intermediates. This pattern contradicts expectations of gradual evolutionary change. It suggests either that adaptation occurred more rapidly than conventional models predict, or that species migrated quickly as environments changed. Further evidence comes from marine sediments. Ocean drilling projects have recovered continuous cores spanning this period, allowing researchers to analyze changes in microscopic marine organisms over time. These cores reveal something unexpected: periodic pulses, where many species disappear simultaneously, followed by rapid diversification of survivors. These patterns occur too frequently to be explained by known meteorite impacts. Some researchers have proposed that Earth's passage through different regions of the galaxy might expose the planet to varying levels of cosmic radiation, potentially affecting mutation rates and even climate. This controversial hypothesis remains unproven, but it attempts to explain synchronous evolutionary changes occurring across widely separated regions, a pattern difficult to account for with conventional mechanisms. The fossil record from Africa during this period presents its own mysteries. The continent was home to a remarkable diversity of apes, with numerous species living in forests across the equatorial regions. Conventional wisdom long held that human ancestors diverged from other apes around 5 to 7 million years ago. But recent discoveries have complicated this timeline, suggesting earlier separations. Fossils like Sahelanthropus chadensis, dated to around 7 million years ago, already show features associated with bipedalism. This pushes the human-chimpanzee split further back, perhaps to 8 to 9 million years ago or earlier. If correct, this revised timeline means our earliest ancestors were evolving during the late Miocene period we're exploring, a significantly earlier emergence than previously believed. Even more puzzling are fragmentary fossils from Kenya and Greece that hint at bipedal apes living 9 to 10 million years ago. These remains are too incomplete for definitive classification, but they raise intriguing possibilities. Could multiple lineages of apes have independently evolved bipedal locomotion? Might our family tree be more complex than the linear progression often depicted? These questions remain actively debated. The late Miocene also presents us with numerous examples of convergent evolution, where unrelated species develop similar adaptations in response to similar environmental pressures. In grasslands across multiple continents, we find mammals evolving long legs, high-crowned teeth, and specialized digestive systems. These similar adaptations emerged independently in lineages that had been separated for millions of years. The synchronicity of these adaptations is striking. It suggests that environmental changes were occurring simultaneously across widely separated regions, a global pattern requiring explanation. Climate models indicate that grassland expansion during this period was indeed a global phenomenon, driven by declining atmospheric carbon dioxide and changing precipitation patterns. But questions about the timing and pace remain. Particularly puzzling is evidence that some evolutionary adaptations appear slightly before the environmental conditions they respond to. It's as if certain species were pre-adapting to changes that hadn't yet fully manifested. This pattern has led some researchers to propose that animals might respond to subtle environmental signals undetectable in the fossil record, perhaps changes in plant chemistry that preceded visible ecosystem transformation. Others suggest more controversial possibilities, that evolutionary change sometimes precedes environmental pressure through mechanisms we don't yet understand, or that our dating methods contain systematic errors. The fossil record from South America during this period adds another layer of mystery. The continent remained isolated, allowing unique mammal lineages to evolve without competition from North American forms. This evolutionary laboratory produced remarkable creatures: giant ground sloths, terror birds, and distinctive ungulates, unlike anything alive today. Their adaptations often paralleled those on other continents while following distinctive paths. But the timing of certain South American adaptations doesn't always align with what we know about the continent's climate history. Some grassland specialists appear before extensive grasslands are thought to have developed. This discrepancy could indicate that our climate reconstructions are incomplete, that these species were responding to localized conditions not captured in broader models, or that other factors influenced their evolution. Perhaps the most enigmatic fossils from this period are those that seem to appear suddenly, without clear ancestors in the geological layers below. These ghost lineages suggest either that significant fossil deposits remain undiscovered or that our understanding is incomplete. One example is the appearance of certain bovid species, relatives of modern cattle and antelopes, that emerge in the fossil record with their distinctive characteristics already established, without the intermediate forms we would expect. Conventional explanation suggests these intermediates existed, but haven't been found, the so-called preservation bias of the fossil record. But the pattern occurs with suspicious frequency during this particular time period. This has led some researchers to propose more controversial hypotheses, that evolution sometimes proceeds in rapid bursts that are unlikely to be captured in fossils, or that environmental stresses can accelerate genetic change. As we conclude this examination of initial evidence, we're left with more questions than answers. The conventional narrative of gradual climate-driven change explains many observations from the late Miocene, but anomalies persist. These inconsistencies don't necessarily invalidate established science, but they suggest our understanding remains incomplete. The fossil record preserves only fragments of life's history, leaving vast unknowns between these preserved moments. What if the story of life 10 million years ago is more complex than we've recognized? What if forces beyond current scientific consensus influenced evolution during this critical period? In the next section, we'll explore one of the most controversial hypotheses, that cosmic factors may have played a role in accelerating evolutionary change during the late Miocene. Before we continue, remember to subscribe if you enjoy stories that blur the line between myth and reality. Every week we reveal something new about the world you thought you knew. Chapter 5. The Cosmic Connection. The conventional narrative of Earth's history 10 million years ago presents a world shaped primarily by familiar forces, climate change, continental drift, and evolutionary adaptation. But anomalies in the fossil record suggest additional factors might have been at work. The most controversial hypothesis proposes that cosmic events influenced Earth's evolution during the late Miocene. While speculative, this theory attempts to explain patterns that conventional models struggle to account for. Consider the curious case of the Valesian crisis, a major extinction event that occurred approximately 9.6 million years ago in Europe. During this event, many forest-dwelling species disappeared suddenly, replaced by grassland-adapted forms. Traditional explanations cite climate change as the primary driver, but the abruptness of the transition has led some researchers to question whether additional factors might have contributed to this ecological reorganization. One controversial theory suggests Earth may have experienced an episode of elevated cosmic radiation during this period. Our solar system orbits the galactic center, occasionally passing through regions of higher radiation density. If Earth traversed such a region during the late Miocene, it might have temporarily increased mutation rates in living organisms. This acceleration could potentially explain the rapid evolutionary changes observed in multiple lineages simultaneously. The evidence for this hypothesis remains circumstantial. Certain geological formations preserve isotope ratios that might indicate periods of increased cosmic radiation. But alternative explanations for these chemical signatures exist. More compelling is the synchronicity of evolutionary changes across widely separated regions. Species on different continents developed similar adaptations within the same relatively narrow time frame, a pattern that suggests a global trigger. Conventional science attributes this synchronicity to global climate change, but the fossil record shows these adaptations sometimes appearing slightly before the environmental conditions they respond to, a curious reversal of cause and effect. Could cosmic radiation have altered Earth's climate through mechanisms like increased cloud formation? Might it have directly influenced evolution through elevated mutation rates? These possibilities remain at the speculative fringe of paleontology. Another puzzling pattern emerges when examining extinction events during this period. While mass extinctions are well documented at other points in Earth's history, the late Miocene witnessed what scientists call turnover pulses. These aren't catastrophic die-offs, but rather periods of accelerated species replacement. Old forms disappear as new variations emerge with unusual rapidity. The mechanism behind these pulses remains debated. Traditional explanations focus on climate oscillations or competitive dynamics between species, but the global nature of these pulses, affecting multiple continents simultaneously, hints at a more universal trigger. Some researchers have proposed that periodic meteor showers might explain these patterns. When Earth passes through certain regions of space, it encounters more debris, resulting in increased impacts. While no major impact craters dating precisely to this period have been conclusively identified, smaller meteorite strikes wouldn't necessarily leave recognizable craters, especially after millions of years of erosion and geological activity. The tektite record presents another anomaly. Tektites are glass objects formed when meteorite impacts melt terrestrial rock, which cools rapidly as it's ejected into the atmosphere. They provide evidence of impacts even when craters have disappeared. Curiously, several tektite fields have been dated to the late Miocene period. The distribution patterns of these fields don't align with any known impact structures, creating a geological puzzle. Could these tektites represent evidence of impacts whose craters have been obscured by time? Or might they have resulted from unusual volcanic processes that mimicked impact characteristics? The debate continues. The fossil record itself presents contradictions during this period. In some locations, we find evidence of gradual evolutionary change, with clear transitional forms linking ancestral species to their descendants. In others, we see what paleontologists call punctuated equilibrium. Long periods of stability interrupted by rapid changes. The late Miocene seems to feature an unusual number of these punctuated events. This pattern is particularly evident in certain mammal lineages. Horse evolution, for instance, shows relatively stable periods interrupted by rapid diversification events that produced multiple new species within geologically brief timeframes. Similar patterns appear in proboscidean evolution, elephants and their relatives, bovid diversification, antelopes and cattle, and the emergence of new carnivore forms. The synchronicity across unrelated groups raises questions. One explanation involves environmental thresholds, points at which gradually changing conditions finally trigger rapid biological responses. This model preserves the mechanism of natural selection while accounting for apparent evolutionary jumps. But some researchers suggest more radical possibilities, including periods of elevated mutation rates driven by external factors. The evidence remains insufficient to confirm or refute these more controversial hypotheses. Perhaps the most puzzling aspect of the late Miocene fossil record involves what paleontologists call ghost lineages, evolutionary lines whose existence is inferred but for which physical evidence is sparse or absent. These missing pieces in the fossil record are particularly common during this period. We find ancestors and descendants, but the intermediate forms are frequently absent, as if pages have been torn from Earth's biographical record. The conventional explanation attributes these gaps to preservation bias. Fossilization requires specific conditions, and the odds of any individual organism becoming preserved are infinitesimally small. Yet the pattern of missing transitional forms appears with suspicious frequency during the late Miocene. This has led some researchers to suggest that evolution might have proceeded more rapidly during this period. If evolutionary change accelerated temporarily, transitional forms might have existed for shorter timeframes, reducing their chances of entering the fossil record. But what might cause such acceleration remains speculative. The geographic distribution of fossil finds adds another layer of complexity. We discover abundant fossils in certain regions, while others yield almost nothing from this period, creating a patchwork understanding. These geographic biases reflect both the conditions necessary for fossil preservation and the uneven distribution of paleontological research globally. Some potentially crucial regions remain virtually unexplored. Central Asia, for instance, likely played a pivotal role in mammalian evolution during this period, but remains incompletely studied. The same applies to large portions of Africa, where early hominin evolution was unfolding. These gaps in our knowledge create space for competing interpretations of the late Miocene world. As new regions yield their fossil treasures, our understanding continues to evolve, sometimes in surprising directions. One recent discovery that challenges conventional timelines comes from the Afar region of Ethiopia. Fossil teeth dated to approximately 9.7 million years ago show characteristics previously believed to have evolved much later. If confirmed, this finding would push back the emergence of certain hominin traits by more than 2 million years. It suggests either parallel evolution in multiple lineages or a much earlier divergence than previously recognized. Similar timeline revisions have occurred repeatedly in paleontology. The history of the field is largely one of pushing events further back in time as new discoveries fill gaps in our knowledge. This pattern raises an intriguing possibility. Might other evolutionary innovations we associate with later periods have emerged during the late Miocene? Could the world 10 million years ago have been more complex than we've imagined? As we continue to explore this lost world, we must remain open to evidence that challenges established narratives. The most significant discoveries often emerge at the boundaries where conventional explanations falter. Chapter 6: Echoes in Myth and Memory. The scientific evidence we've examined thus far comes from traditional sources: fossils, geological formations, isotope studies. But there exists another category of information, more controversial but potentially illuminating: the mythological record. Human societies worldwide preserve ancient stories that some researchers interpret as distorted memories of real events. Could any of these narratives contain echoes of the late Miocene world? The evidence is highly speculative but fascinating. Most human myths are clearly symbolic or metaphorical, but certain recurring themes across widely separated cultures have led some scholars to propose they might preserve extremely ancient observations passed down through countless generations. The most relevant category involves stories of dramatic environmental change, myths describing transformed landscapes, altered climates, or the appearance and disappearance of certain animals. Consider the widespread myths of ancestral times, when the world was different, when animals could speak, when humans and beasts lived differently, when the landscape itself had another character. Conventional interpretation views these as purely symbolic narratives or explanations for observed natural phenomena. But some researchers have proposed a more literal interpretation, that they preserve dim memories of actual environmental transitions. This hypothesis faces an obvious challenge. The late Miocene occurred millions of years before modern humans evolved. Even our earliest hominin ancestors with brains capable of language and cultural transmission emerged much later. But proponents suggest these memories might have been encoded in pre-linguistic ways, transmitted through behavioral adaptations that eventually found expression in language once humans developed speech. The concept is speculative, but not entirely without scientific basis. Epigenetic research has demonstrated that environmental influences can affect gene expression in ways that persist across generations. Could traumatic environmental changes during the late Miocene have left epigenetic markers in our ancestors? Might these have influenced neural development in ways that created predispositions towards certain perceptions or fears? Such mechanisms could potentially explain the cross-cultural prevalence of certain environmental themes in mythology. The widespread fear of large predators, for instance, far exceeds their actual threat to modern humans. More directly relevant are myths describing dramatic landscape transformations. Many cultures preserve stories of lands that were once connected becoming separated, of seas appearing where land once existed. The Mediterranean desiccation events of the late Miocene, when the Mediterranean Sea repeatedly dried up and refilled, represent exactly this kind of dramatic transformation. But they occurred roughly 6 million years ago, far too early for direct human memory. Yet the geological evidence of these events remains visible in the landscape today. Could early humans have observed these features and constructed explanatory narratives that entered the mythological record? Another category of potentially relevant myths involves extinct animals. Some cryptozoologists controversially suggest that certain legendary creatures might represent cultural memories of species that disappeared in the relatively recent past. Most such claims involve Pleistocene megafauna that coexisted with early humans. But a few researchers have proposed more radical interpretations of certain mythical creatures as representing Miocene species that survived later than currently recognized. The scientific consensus firmly rejects such interpretations, emphasizing the vast time gap and lack of physical evidence. But these speculations highlight the human tendency to seek connections between observable phenomena and explanatory narratives. Perhaps more intriguing are myths involving celestial events, stories of objects falling from the sky, of darkness descending, of the sun or moon behaving strangely. Many cultures preserve such accounts. Conventional interpretations link these to observed astronomical phenomena like meteor showers, solar eclipses, or unusual weather events. But might some preserve memories of more dramatic cosmic occurrences? The controversial hypothesis we explored earlier, that Earth may have experienced periods of elevated cosmic influence during the late Miocene, finds curious parallels in these mythological themes. None of this constitutes scientific evidence in the conventional sense, but these cultural patterns raise interesting questions about how environmental events become encoded in human consciousness across generations. Moving beyond mythology, we find more concrete but equally controversial evidence in what researchers call out-of-place artifacts or geological anomalies, objects or formations that seem inconsistent with their surroundings. Most such claims involve misidentifications or misinterpretations. Natural processes can create remarkably regular or artificial-looking patterns that are nonetheless entirely geological in origin. But occasionally, genuinely puzzling discoveries emerge. Objects found in geological strata where they seemingly shouldn't exist. Formations that defy conventional explanation, patterns that suggest complexity where simplicity was expected. One category involves trace fossils, impressions left by organisms rather than the preserved organisms themselves. These can be particularly difficult to interpret accurately, especially when they're fragmentary or unusual. Several controversial discoveries involve what appear to be footprint-like impressions in rock layers dated to the late Miocene. Conventional interpretations attribute these to known animals or to geological processes mimicking footprints. But some researchers argue that certain specimens don't match any known species from the period. These claims remain highly contested, with mainstream science generally favoring more conservative interpretations. Similarly controversial are certain stone formations discovered in late Miocene deposits that display unusual patterns of fracture or wear. Some fringe researchers have suggested these might represent primitive tools. The scientific consensus firmly rejects such interpretations, noting that natural processes can create remarkably tool-like formations. The human tendency to see patterns and intention where none exists, pareidolia, further complicates assessment. Less controversial but equally puzzling are certain micro-paleontological findings, microscopic fossils that show unexpected characteristics or appear in unexpected locations. These tiny remnants can reveal surprising ecological relationships. For instance, certain microfossils indicate the presence of ecosystems that shouldn't have existed in particular locations based on climate models of the late Miocene. These discrepancies suggest our understanding remains incomplete. The distribution of certain plant pollens during this period presents similar puzzles. We find evidence of plant species growing in regions where climate reconstructions suggest they shouldn't have thrived. These botanical anomalies could indicate localized microclimates not captured in broader models, or they might suggest our climate reconstructions for the period require revision. Perhaps the most significant category of out-of-place evidence involves species appearing earlier in the fossil record than evolutionary models predict. These chronological anomalies force reconsideration of established timelines. Recent discoveries in Germany, for instance, identified primate fossils with characteristics previously associated with much later species. If confirmed, these findings would require revisions to evolutionary timetables. Similar timeline revisions have occurred repeatedly in paleontology. The emergence of bipedalism, tool use, and other significant adaptations have all been pushed back as new evidence emerges. This pattern suggests our understanding of the late Miocene remains provisional. The world of 10 million years ago may have been more complex, more dynamic, and more surprising than current models suggest. The most controversial interpretations of these anomalies propose that certain advanced adaptations may have emerged earlier than conventionally recognized, only to disappear again before re-emerging later. Mainstream science generally rejects such interpretations, emphasizing the principle of parsimony, that simpler explanations should be preferred unless evidence compels more complex ones. Yet the history of paleontology includes numerous examples where conventional wisdom was overturned by unexpected discoveries. The complexity of evolutionary history continues to surprise even the most knowledgeable researchers. As we sift these controversial claims from more established knowledge, we must maintain both skepticism and openness. The most significant advances often emerge from investigating anomalies that don't fit neatly into existing frameworks. The late Miocene world remains partially hidden from us, preserved in fragments and glimpses. What we know with certainty represents merely a fraction of what once existed. In this space of partial knowledge, both rigorous science and more speculative inquiry have roles to play. By examining conventional evidence alongside more controversial claims, we gain a more complete picture of this lost world. Chapter 7: A World on the Edge. As we've journeyed deeper into the late Miocene, a picture emerges of a world balanced on a knife edge of change. Climate systems were shifting, continents were moving, ecosystems were transforming, and life was adapting in remarkable ways. The stakes of understanding this period extend far beyond academic curiosity. The late Miocene represents Earth's most recent experience with atmospheric carbon dioxide levels approaching those we're creating today. It offers crucial insights into our possible future. 10 million years ago, CO2 concentrations were declining from earlier peaks, but remained higher than pre-industrial levels. The world was generally warmer, with different precipitation patterns and sea levels approximately 40 meters higher than today. If we correctly understand the relationship between atmospheric chemistry and climate during this period, it could significantly refine our models of current climate change. The implications for human civilization would be profound. But if the anomalies we've explored indicate our understanding remains incomplete, the uncertainty cuts both ways. Climate change might progress differently than current models predict, potentially more gradually, but possibly more abruptly. The late Miocene also witnessed substantial extinction events, not as dramatic as the dinosaur killing impact 66 million years ago, but significant nonetheless. Understanding these events has direct relevance to our current biodiversity crisis. Species disappeared during this period for various reasons: changing environments, new competitive relationships, novel diseases. But the pattern of extinction wasn't uniform across all groups or regions. Some lineages proved remarkably resilient despite dramatic environmental changes. Others vanished despite seemingly minor shifts in conditions. This variable response challenges simple explanations and complicates predictions about modern extinction rates. If we can identify what made certain species vulnerable while others adapted successfully, we might better assess which modern species face the greatest extinction risk. This knowledge could guide conservation priorities in our resource-limited world. But the complexity of late Miocene extinction patterns suggests simplistic approaches will prove inadequate. The interaction between environmental change, ecological relationships, and evolutionary adaptation created outcomes that remain difficult to predict. Perhaps most significantly, the late Miocene offers insights into how rapidly ecosystems can transform when pushed beyond certain thresholds. Evidence suggests these transitions sometimes occurred more quickly than gradual models would predict. If modern ecosystems follow similar patterns, we might be underestimating how rapidly environmental change could transform the world around us. Systems we perceive as stable might reorganize dramatically when critical thresholds are crossed. The fossil evidence indicates that once certain tipping points were reached during the late Miocene, ecosystems didn't merely change gradually, they transformed into fundamentally different states, often within timeframes shorter than expected. These ecological regime shifts occurred across multiple regions within similar timeframes, suggesting global triggers rather than localized causes. The synchronicity of these changes represents one of the period's most puzzling aspects. If modern ecosystems follow similar patterns, we might experience synchronous transformations across widely separated regions as climate change progresses. The implications for agriculture, water resources, and human settlement patterns would be profound. This brings us to perhaps the most consequential question raised by late Miocene evidence. How rapidly can life adapt to environmental change? The fossil record provides contradictory answers. In some lineages, we see remarkable adaptive radiation, rapid diversification in response to new conditions or opportunities. Species developed novel features and behaviors within timeframes that seem surprisingly brief. In others, we find evidence of evolutionary conservatism, resistance to change despite altered environments. These species maintained their characteristics until they either found suitable remnant habitats or disappeared entirely. This variable response challenges uniform models of evolutionary adaptation. It suggests that different types of organisms have fundamentally different capacities to respond to environmental change. For modern conservation, this insight suggests that species will not respond uniformly to current climate change. Some may adapt surprisingly well, while others prove unexpectedly vulnerable, despite seeming resilience. The stakes extend to our own species as well. Humans evolved remarkable behavioral flexibility, allowing cultural adaptation to environmental change, but this adaptation assumes changes occur within certain limits and timeframes. If the late Miocene evidence suggests environmental transformations can occur more rapidly than conventional models predict, we might be underestimating the adaptation challenges humanity could face in coming centuries. The controversial cosmic hypothesis we explored earlier, that external factors might have influenced Earth systems during this period, raises the stakes further. If correct, it would suggest additional variables in Earth's climate system. While mainstream science generally rejects such exotic explanations, the synchronicity of changes across separated regions during the late Miocene remains incompletely explained. This gap in understanding has implications for climate prediction. Consider the Mediterranean desiccation events that occurred toward the end of the Miocene. Conventional explanations involve the interaction between tectonic processes and climate change, but questions about timing and mechanism persist. These massive transformations, the repeated drying and refilling of an entire sea, occurred with surprising rapidity in geological terms. If our understanding of the processes involved is incomplete, we might misunderstand similar threshold events today. The late Miocene also witnessed significant changes in ocean circulation patterns as continental configurations shifted. These alterations in oceanic heat transport had global climate implications that reverberated through terrestrial ecosystems. Today, we face analogous concerns about potential changes to ocean circulation systems, like the Atlantic Meridional Overturning Circulation, epoch. The Miocene record suggests such changes could trigger cascading effects through Earth's climate system. But perhaps the most profound insight from the late Miocene involves the complex interplay between multiple Earth systems: atmosphere, oceans, land surfaces, and biosphere. Changes in one domain reverberated through others in complex feedback loops. This interconnectedness created both amplifying and dampening effects. Some initial changes triggered cascades that magnified their impact. Others activated negative feedbacks that limited their consequences. Our current understanding of these feedback mechanisms remains incomplete. If the late Miocene evidence suggests greater complexity than our models incorporate, our climate predictions may contain significant uncertainties in either direction. This uncertainty doesn't justify inaction on climate change, quite the opposite. It suggests the possibility of outcomes both better and worse than current projections, increasing the imperative for precautionary approaches. The biological stakes extend beyond climate effects. The late Miocene witnessed shifting relationships between species, new predator-prey dynamics, altered competitive interactions, changing disease patterns, and novel symbiotic relationships. These ecological reorganizations had evolutionary consequences that shaped the biological world we inhabit today. Understanding these processes helps explain modern biodiversity patterns and species distributions. But more urgently, this understanding informs our assessment of how current ecological disruptions might propagate through time. The consequences of biodiversity loss extend beyond the species that disappear directly. The fossil record shows that when keystone species disappeared during the late Miocene, effects cascaded through ecosystems, sometimes leading to collapse and reorganization. Similar vulnerabilities exist in modern systems for human societies dependent on ecosystem services. From pollination to water purification to climate regulation, these insights carry profound implications. Our well-being remains inextricably linked to ecological stability. As we approach the climax of our exploration into this lost world, one question emerges with particular urgency. What caused the environmental transitions of the late Miocene, and could similar mechanisms operate today? The conventional narrative emphasizes gradual processes, tectonic movements, orbital variations, atmospheric changes, and evolutionary adaptation. But the anomalies we've explored hint at additional factors or mechanisms. If these transitions involved thresholds and tipping points, where gradual change suddenly accelerated, we might be underestimating how rapidly our own world could transform as human activities push against similar boundaries. Recent research on modern climate systems has identified numerous potential tipping elements, components that could change state rapidly when critical thresholds are crossed. The late Miocene may offer historical examples of such transitions, but the most radical possibility raised by our exploration involves factors beyond those commonly incorporated in Earth system models. If cosmic influences periodically affect our planet's climate or biology, our understanding remains incomplete. The scientific consensus firmly rejects such exotic mechanisms in favor of known processes. But the history of science includes numerous examples where conventional wisdom eventually yielded to evidence of previously unrecognized forces. As we conclude this segment of our journey, we find ourselves with more questions than when we began. The world of 10 million years ago, so crucial for understanding our present and future, remains partially veiled in mystery. What forces shaped this pivotal period in Earth's history? Why did so many evolutionary innovations emerge within a relatively brief window? How did ecosystems transform so dramatically, and what triggered these transformations? These questions aren't merely academic. They speak directly to our understanding of Earth's systems and how they respond to change. Knowledge that has never been more relevant than in our current moment of environmental transformation. In the final segment of our exploration, we'll examine the most compelling evidence for various explanations of the late Miocene world. We'll weigh conventional science against more controversial hypotheses, seeking the most complete understanding possible. What we discover may challenge fundamental assumptions about Earth's history. It might alter our perception of evolutionary processes, and it could significantly influence how we interpret our planet's future as human activities transform the world around us. Chapter 8. Threshold World. As we approach the core of our investigation, three compelling theories emerge to explain the patterns observed in the late Miocene. Each interprets the evidence differently, and each carries distinct implications for our understanding of Earth's systems. The first and most conventional theory emphasizes gradual climate change driven by known mechanisms. According to this model, declining atmospheric carbon dioxide levels triggered a cascade of environmental effects that transformed ecosystems worldwide. This gradual cooling led to expanding ice sheets, altered ocean circulation, and changing precipitation patterns. These shifts favored grasslands over forests in many regions, creating new selective pressures that drove evolutionary change. The strength of this theory lies in its adherence to known mechanisms with established evidence. It requires no exotic explanations and aligns with our understanding of how Earth's climate system operates today. But this conventional model struggles to explain certain anomalies we've explored, particularly the apparent synchronicity of changes across widely separated regions and the seemingly abrupt nature of some transitions. The second theory proposes that threshold effects played a more significant role than traditionally recognized. According to this model, gradual changes eventually pushed Earth systems past critical tipping points, triggering rapid transformations. These threshold effects could explain the apparent contradiction between gradual forcing mechanisms and abrupt changes in the fossil record. Systems can absorb pressure until reaching critical points where they suddenly reorganize into different states. Recent research on modern climate systems has identified numerous potential tipping elements, components that can shift states relatively abruptly when certain thresholds are crossed. The late Miocene may have witnessed several such transitions. For instance, evidence suggests the Antarctic ice sheet may have undergone relatively rapid expansion during this period, crossing thresholds where positive feedbacks accelerated the process beyond what initial forcing alone would predict. Similarly, the expansion of grasslands appears to have accelerated once certain thresholds were crossed. Fire frequency, herbivore grazing patterns, and soil chemistry likely created feedback loops that transformed landscapes more rapidly than climate change alone. This threshold model preserves the fundamental mechanisms of conventional theory, while better explaining the patterns of apparent discontinuity in the fossil record. It requires no exotic mechanisms, merely a better understanding of system dynamics. The evidence for threshold effects comes from multiple sources. Sediment cores show abrupt transitions between environmental states. Fossil assemblages change composition rapidly at certain boundaries. Isotope ratios shift dramatically within narrow timeframes. Perhaps most compelling is evidence from modern systems that demonstrates how ecosystems can exist in alternative stable states, switching between them when certain conditions are met. The late Miocene record shows patterns consistent with such transitions. For instance, regions that could support either woodland or grassland appear to have shifted between these states rapidly, rather than existing in intermediate conditions for extended periods. This pattern matches modern observations of ecosystem behavior. The threshold theory also better explains the evolutionary patterns observed in the fossil record, particularly the apparent punctuated equilibrium, where species show stability followed by relatively rapid change. If environmental conditions crossed thresholds that significantly altered selection pressures, evolutionary responses would accelerate. Species well adapted to previous conditions would face sudden disadvantages, driving rapid adaptation or extinction. The third and most controversial theory suggests that external triggers, possibly cosmic in nature, periodically influenced Earth systems during the late Miocene, synchronizing changes across widely separated regions. This hypothesis proposes that Earth's passage through different regions of the galaxy might have exposed the planet to varying levels of cosmic radiation, potentially affecting climate through cloud formation or directly influencing mutation rates. The evidence for this cosmic hypothesis remains circumstantial at best. Certain isotope signatures in geological formations suggest periods of altered cosmic ray flux, but alternative explanations for these signatures exist. More compelling is the synchronicity of changes across separated regions, a pattern difficult to explain through gradual climate change alone, particularly before global atmospheric circulation was as well understood as it is today. If cosmic factors periodically affected Earth's climate or biology, it would explain why certain evolutionary innovations appeared nearly simultaneously across multiple continents, despite geographical isolation. But mainstream science remains skeptical. The scientific consensus strongly favors the threshold model as the most parsimonious explanation, one that accounts for observed patterns without requiring exotic mechanisms. It represents a refinement of conventional understanding rather than a rejection. But science progresses by questioning established models when they fail to fully explain observations. The anomalies in the late Miocene record continue to inspire research that may eventually resolve these competing interpretations. The distinction between these theories isn't merely academic. Each carries different implications for how we understand Earth systems and their response to change, knowledge directly relevant to our current climate situation. If the threshold model best explains late Miocene transitions, it suggests modern ecosystems might transform more abruptly than gradual models predict when critical boundaries are crossed. This possibility demands greater precaution in our approach to environmental change. Modern climate models increasingly incorporate these threshold effects, but significant uncertainties remain about where these boundaries lie and how abruptly systems might respond when they're crossed. The late Miocene record offers potential insight into these questions, showing how Earth's systems responded to similar pressures in the past. But extracting clear lessons requires resolving the competing interpretations we've examined. Recent research has attempted to distinguish between these theories using new analytical techniques. Advanced isotope studies, improved dating methods, and computational modeling have all contributed to a more nuanced understanding. Perhaps most promising are techniques that allow finer temporal resolution in the geological record. Traditional methods often couldn't distinguish between changes occurring over thousands versus hundreds of years, a crucial distinction for identifying threshold effects. New approaches using varves, annual sediment layers, speleothems, cave formations, and other high-resolution proxies have revealed that many transitions occurred more rapidly than previously recognized, supporting the threshold interpretation. Similarly, improvements in spatial coverage have demonstrated that environmental changes often propagated across regions in patterns consistent with climate system dynamics rather than simultaneously worldwide, weakening the case for cosmic triggers. As evidence accumulates, the scientific consensus has increasingly embraced the threshold model while incorporating elements of both conventional gradual change and more rapid transitions. This synthesis better explains the complex patterns observed, but significant questions remain. The apparent synchronicity of some changes across widely separated regions continues to challenge simple explanations. The abruptness of certain transitions suggests mechanisms not fully captured in current models. These lingering mysteries have inspired new research directions that promise to further clarify the dynamics of the late Miocene world and their implications for our understanding of Earth's systems. Chapter 9. Breaking the Code. Recent scientific breakthroughs have transformed our understanding of the late Miocene, resolving some long-standing puzzles while revealing new complexities. Advanced analytical techniques now allow us to extract information from fossils and sediments that was previously inaccessible. Perhaps most significant are developments in ancient DNA analysis. While DNA rarely survives millions of years, new methods can recover fragments from exceptionally preserved specimens, offering unprecedented insights into genetic relationships and evolutionary processes. In 2019, researchers successfully recovered protein sequences from a 1.7 million-year-old rhinoceros tooth. This breakthrough suggests similar techniques might eventually extract molecular information from late Miocene specimens, directly testing evolutionary hypotheses. Meanwhile, advances in isotope geochemistry have revolutionized our ability to reconstruct ancient environments. By analyzing the ratios of various isotopes in fossils and sediments, scientists can determine temperatures, precipitation patterns, and even dietary habits with remarkable precision. These techniques have revealed that late Miocene climate fluctuations were more complex than previously recognized. Rather than a simple cooling trend, the period featured oscillations of varying amplitude and frequency, creating a constantly shifting selective landscape. Similarly, microscopic analysis of fossil teeth has demonstrated that dietary adaptations often preceded visible changes in tooth morphology. Animals were behaviorally adapting to changing food resources before their bodies physically evolved to optimize these new diets. This pattern suggests that behavioral flexibility may have played a more significant role in evolutionary responses than previously recognized, an insight with implications for predicting how modern species might adapt to current environmental change. Advanced computer modeling has also transformed our understanding of late Miocene climate dynamics. By simulating atmospheric and oceanic circulation with unprecedented detail, researchers have identified mechanisms that could transmit environmental changes across distant regions. These models demonstrate how alterations in one region could trigger cascading effects worldwide through teleconnections in Earth's climate system. Such mechanisms help explain the apparent synchronicity of changes without requiring exotic triggers. For instance, shifts in tropical ocean temperatures could alter global atmospheric circulation patterns, affecting precipitation across multiple continents simultaneously. These connections weren't fully appreciated in earlier interpretations of the fossil record. Equally significant are advances in our understanding of ecological networks. Modern research reveals how changes affecting keystone species can propagate through ecosystems in ways that appear simultaneous, but actually represent linked causal chains. These insights help explain why certain types of organisms show coordinated responses to environmental change despite having no direct connection. Their shared position in ecological networks means they experience similar selective pressures when keystone species or resources change. But perhaps the most transformative recent advance involves our understanding of evolutionary processes themselves. Traditional models emphasized gradual change through natural selection, but newer research highlights additional mechanisms. Epigenetic changes, alterations in gene expression rather than genetic code itself, can enable rapid adaptation to new conditions. These modifications can even be inherited across generations, allowing quicker responses than genetic evolution alone. Similarly, hybridization between closely related species can introduce genetic variations that accelerate evolutionary change. Evidence suggests such hybridization occurred frequently during the late Miocene, as changing environments brought previously separated populations into contact. These mechanisms help explain the apparent evolutionary leaps in the fossil record without requiring either implausibly rapid genetic change or gaps in preservation. They represent middle ground between gradual and punctuated models. Yet despite these advances, significant paradoxes remain in our understanding of the late Miocene world. Three in particular continue to challenge researchers and inspire new investigations. The first involves the carbon paradox. Evidence suggests atmospheric carbon dioxide levels were declining during this period, yet certain regions show evidence of warming rather than cooling. This contradicts our understanding of greenhouse gas effects. Recent research proposes that changes in Earth's albedo, reflectivity, due to shifting vegetation patterns and ice coverage, might explain this apparent contradiction. Less reflective surfaces could have trapped more heat despite lower greenhouse gas concentrations. Alternatively, changes in oceanic circulation might have redistributed heat differently across the planet, causing some regions to warm despite overall cooling. These hypotheses remain actively investigated as scientists seek to resolve the carbon paradox. The second major paradox involves evolutionary timing. In several lineages, adaptations appear in the fossil record before the environmental conditions they supposedly respond to. This apparent reversal of cause and effect challenges conventional evolutionary models. One explanation involves missing evidence. The environmental changes might have occurred earlier than our current record indicates. Alternatively, these adaptations might have evolved for different reasons initially, later proving advantageous when environments changed. This concept of exaptation, where structures evolved for one purpose are co-opted for another, is well established in evolutionary biology. It might explain why some species appeared pre-adapted to conditions that emerged during the late Miocene. The third paradox involves extinction patterns. Some apparently well-adapted species disappeared during this period, while more specialized ones survived. This contradicts the expectation that generalists should better weather environmental change. Recent research suggests that ecological relationships might explain this paradox. Even well-adapted species can disappear if their prey, predators, or symbiotic partners cannot adjust to changing conditions. Resilience depends on entire ecological networks, not just individual adaptations. These unresolved paradoxes highlight how much remains to be discovered about the late Miocene world. But rather than undermining scientific understanding, they drive research forward, inspiring new investigations and analytical approaches. Perhaps the most exciting recent development involves the application of machine learning to paleontological data. By identifying patterns too subtle for human recognition, these techniques have revealed previously undetected relationships and trends. One application has identified subtle morphological changes that precede major evolutionary transitions, early warning signs of adaptation that weren't previously recognized. This allows more precise tracking of how species responded to environmental pressure. Another has revealed correlations between seemingly unrelated environmental proxies, suggesting connections between Earth systems that weren't previously understood. These discoveries have prompted reinterpretation of causal relationships during the late Miocene. Together, these advances have transformed our understanding of this pivotal period from a relatively simple narrative of gradual climate change to a complex story of interacting systems with multiple feedback loops, threshold effects, and unexpected connections. What emerges is a picture of Earth as an integrated system where changes in one component propagate through others in ways both predictable and surprising. This perspective has profound implications for how we interpret both past and future environmental change. The late Miocene increasingly appears to represent a threshold world, a planet poised between states, where relatively small changes could trigger cascading effects through interconnected systems. This characteristic made it particularly sensitive to both gradual pressures and sudden triggers. Modern Earth may occupy a similar threshold state, where human activities push against planetary boundaries with consequences that might manifest suddenly rather than gradually. The late Miocene offers potential insight into how such threshold systems behave, but extracting clear lessons requires acknowledging both what we know and what remains uncertain. The paradoxes we've explored highlight the limitations of our current understanding while pointing toward promising research directions. As we prepare to integrate these insights into a coherent understanding of the late Miocene world, we must embrace both the solid evidence and the remaining mysteries. Together, they tell a story more nuanced and revealing than either alone. Chapter 10. The Threshold Planet. We began this journey seeking to understand a lost world that existed 10 million years ago, a planet both familiar and alien, where the continents we know had formed but were populated by creatures and ecosystems now vanished. Throughout our exploration, we've encountered evidence that challenges simple narratives. We've examined competing theories that interpret this evidence differently. We've considered both established science and more speculative hypotheses. Now we arrive at what the evidence most strongly suggests. The late Miocene represented a critical threshold period in Earth's history, a time when the planet's systems were transitioning between states, creating conditions that would shape all subsequent life. This threshold nature explains the seemingly contradictory patterns in the fossil record: periods of stability interrupted by rapid change, synchronous transitions across distant regions, and evolutionary innovations that appear almost simultaneously in unrelated lineages. Earth's climate system was shifting from one stable state toward another. Ocean circulation patterns were reorganizing as continental positions changed. Atmospheric chemistry was altering as carbon dioxide levels declined and vegetation patterns shifted. These changes didn't proceed at uniform rates. Instead, they followed the pattern characteristic of complex systems approaching thresholds, long periods of apparent stability punctuated by relatively rapid transitions when critical boundaries were crossed. This pattern manifested differently across regions. Some areas transformed rapidly when local conditions crossed critical thresholds. Others changed more gradually, but all were components of an interconnected planetary system moving toward a new equilibrium. The evidence for this threshold interpretation comes from multiple sources. Sediment records show abrupt transitions between states. Fossil assemblages change composition rapidly at certain boundaries. Isotope ratios shift dramatically within narrow timeframes. But perhaps most compelling is how this model integrates seemingly contradictory observations into a coherent framework. It explains both gradual and abrupt changes as different manifestations of the same underlying process, a complex system approaching and crossing multiple thresholds. This interpretation doesn't require exotic triggers or unknown mechanisms. It simply recognizes that Earth's interconnected systems don't always respond linearly to forcing. Small changes can cascade through feedback loops to produce large effects when thresholds are crossed. Modern climate science has increasingly identified similar dynamics in our current Earth system. Components like the Amazon rainforest, West Antarctic ice sheet, and Atlantic meridional overturning circulation all display threshold behaviors where gradual pressure can trigger abrupt changes. The late Miocene offers a natural experiment in how such threshold systems behave, valuable insight as human activities push against similar boundaries today. But extracting clear lessons requires understanding the unique context of that ancient world. 10 million years ago, atmospheric carbon dioxide levels were declining gradually from earlier peaks. Today, they're rising rapidly due to human activities. This difference in rate may be crucial for understanding how Earth's systems will respond. Similarly, the late Miocene threshold transitions occurred in a world with different continental configurations, ocean circulation patterns, and biological communities than exist today. These differences limit direct comparisons, while still offering valuable insights. Perhaps the most significant lesson involves how biological communities responded to these threshold transitions. The fossil record shows varying capacity for adaptation among different types of organisms. Some species disappeared when their environments transformed. Others migrated to regions where suitable conditions persisted. Still others adapted through behavioral flexibility, physiological tolerance, or evolutionary change. This variable response challenges simplistic predictions about how modern biodiversity will respond to current environmental change. It suggests both greater resilience and greater vulnerability than linear models might predict. The late Miocene also offers insight into how ecosystems reorganize after crossing thresholds. New communities didn't simply replace old ones intact, they assembled from components of previous systems combined with evolutionary innovations. These novel ecosystems often function differently from those they replaced, with altered energy flows, nutrient cycling, and ecological relationships. The emergence of grassland systems represents perhaps the most significant example, creating new evolutionary opportunities. Our own lineage emerged from this threshold world. The shifting mosaic of forests and grasslands created selective pressures that favored adaptable primates, those that could exploit both environments and adjust to changing conditions. The human capacity for behavioral flexibility, technological innovation, and cultural adaptation likely has roots in these late Miocene environmental transitions. Our ancestors were those who survived and thrived in a world of crossing thresholds. This perspective transforms how we understand both the past and our current moment. Earth has experienced threshold transitions before. What makes our time unique is not that systems are changing, but the unprecedented rate of change driven by human activities. The late Miocene transitions unfolded over thousands to tens of thousands of years, timeframes that allowed at least some evolutionary adaptation. Current changes occur over decades to centuries, limiting biological responses primarily to migration and phenotypic plasticity. This rate difference has profound implications for biodiversity, ecosystem services, and ultimately human well-being. It suggests both greater risks and greater responsibilities than we might otherwise recognize. But the threshold perspective also offers hope. If Earth's systems respond to thresholds rather than changing linearly, reducing pressures before critical boundaries are crossed could prevent the most severe transitions, even if some change is inevitable. This understanding has emerged only recently, as paleoclimate records, ecological studies, and complex systems theory have converged to reveal Earth's threshold dynamics. It represents a fundamental shift in how we understand planetary change. The lost world of the late Miocene was not simply a different configuration of familiar elements. It was a planet in transition, crossing multiple thresholds that would shape all subsequent life. Understanding this threshold nature changes how we interpret both past and future. When we look at seemingly abrupt transitions in the fossil record, we're not seeing incomplete preservation or mysterious external triggers. We're witnessing the natural behavior of complex systems, crossing critical boundaries after long periods of gradual pressure. This threshold model resolves many long-standing puzzles in paleontology. It explains apparently synchronized changes across distant regions through interconnected Earth systems rather than simultaneous external forces. It accounts for the pattern of punctuated equilibrium observed in many evolutionary lineages, where species show stability followed by relatively rapid change. These patterns emerge naturally from threshold dynamics without requiring special mechanisms. And critically, it integrates our understanding of biological evolution with Earth system science. revealing how intimately life and planet have shaped each other through their interconnected thresholds and feedbacks. This integration represents the most significant recent advance in our understanding of Earth's history. It moves beyond treating climate, geology, and biology as separate domains toward recognizing them as components of a single integrated system. The world 10 million years ago offers a crucial case study in how this integrated Earth system responds when multiple components approach thresholds simultaneously. The lessons remain directly relevant as human activities push against similar boundaries today. We stand at our own threshold moment, a time when human decisions will determine which planetary boundaries are crossed and which remain respected. The late Miocene offers both warning and guidance as we navigate these choices. It reminds us that Earth systems have inherent limits, beyond which relatively rapid transformations occur. It shows that crossing multiple thresholds simultaneously can trigger cascading changes across interconnected systems. But it also demonstrates the remarkable resilience and adaptability of life. Throughout Earth's history, species have survived threshold transitions through migration, phenotypic plasticity, and evolutionary innovation. The difference today is time frame. Natural threshold transitions unfolded over millennia. Our activities compress similar changes into centuries or decades, limiting adaptive responses, especially for long-lived and slow-reproducing species. As we conclude our journey through this lost threshold world, we find ourselves with greater understanding of both our past and our possible futures. The late Miocene was not merely a different time, it was a planet in transition that shaped all that followed. The world 10 million years ago exists now only in fragments, in scattered fossils, in chemical signatures preserved in ancient soils, in the genetic codes of living descendants. Yet its influence surrounds us, having shaped the planet we inhabit today. Our grasslands and savannas, our grazing mammals and predatory carnivores, the distribution of our forests and deserts, all bear the imprint of those ancient threshold crossings. Even our own bodies carry adaptations forged in that transitional world. When you look at a modern horse, you're seeing the culmination of evolutionary processes that accelerated during the late Miocene. Its single toe, high-crowned teeth, and digestive adaptations all emerged as grasslands expanded across continents. Similarly, the human capacity for upright walking likely has roots in the mosaic environments of that threshold world, where adaptability between forest and open country conferred survival advantages on our distant ancestors. The late Miocene teaches us that Earth is not simply a backdrop against which life evolves, but an integrated system where geological, atmospheric, oceanic, and biological components interact through complex feedbacks and thresholds. This perspective transforms how we understand our current moment. We aren't merely changing Earth's chemistry and biology, we're pushing an integrated system toward multiple thresholds whose crossings may trigger cascading transformations. The choice before us isn't whether Earth will change. Change is inherent in planetary systems. The question is whether we push it across thresholds that lead toward states less conducive to human flourishing and biodiversity. Understanding these threshold dynamics doesn't diminish our challenges, but it clarifies our choices. It reveals both the risks of crossing critical boundaries and the possibility of maintaining systems within sustainable limits through informed action. As we continue exploring our planet's extraordinary history and uncertain future, remember that you're witnessing the latest chapter in an ongoing story, one where life and planet have continually shaped each other through their interconnected thresholds and feedbacks. If this journey through Earth's threshold past has sparked your curiosity about our planetary future, join us for our next exploration. Subscribe to continue unraveling the complex story of our extraordinary world, a planet shaped by thresholds, where the past echoes into our present and future.